Hello. In the previous session, we studied derivatives, differentiability, continuity, and some related questions. And the most important problem we consider is the tangent problem. And we know that the derivative is the slope of the tangent line, right, to the graph at the given point. So when you look at the derivative, you might think about, yeah, that is the slope of the tangent line. That is instantaneous rate of change, right? And okay, so again, right, that is derivative. So this is very important. We need to solve the tangent line, and in that section we study derivative of some specific power functions, right? We study, I think, x squared, derivative of x to negative 1, and derivative of x to 1.5, right? We know derivative of x squared is 2x, derivative of x to negative 1 is negative x to negative 2, and derivative of this guy is 1.5 x to 1.5, or this is negative 1 over x squared. This is 1 over 2 square root of x. So, this is about the power rule, right? That is power function. And in this video, we study, the power rule, the general power rule, how to find derivative of a power function. We don't prove anything in this video, okay? So sometimes we just need to accept the formula and then apply that correctly. Agree? And I want to mention one thing, right? Differentiation rules are very important, not only in Calculus 1, in Calculus 2, and almost everywhere. If you go to Calculus 3 or, something else, right? You need to find derivatives all the time. So please practice more and more and more, okay? That is the only way to measure this, differentiation rule, okay? So let's talk about the power rule. If you have function x to the p and you consider the derivative of x to the p, sometimes they write dx x to the p, okay? So this is another notation of the derivative. This is p x to p minus 1. So in order to remember this, right, so you just take p out of the differentiation operation and then you reduce the power by 1. Okay? So if you use this rule for this function, okay, let's check again, right? Derivative of x squared is what? The power is 2. I will print the power down here. I have 2 times in here, and then x. I reduce the power by 1. I get 2 minus 1, which is 2x. You see, we get exactly 2x in here. All right? All right, let's talk about, 1 over x. Derivative. 1 over x is x to negative 1. Don't forget that. Sometimes we need to convert to power function, to power form, okay? And you take the power down, which is negative 1, and then you reduce the power by 1. You get negative x to negative 2, and that is negative 1 over x squared. You see? That's what we have in here. Okay? And then square root of x, derivative. The square root is x to 1/2. you bring the power down 1/2 in here, and then you reduce the power by 1 minus 1. You get 1/2 x2 negative 1/2, because 1/2 minus 1 is negative 1/2, right? And that is 1 over 2 x2 1/2, or 1 over 2 square root of x. So this is another kind of technique, right? We convert fractional to power. We convert a radical function to power function. Okay, we use that a lot. Agree? Now, if you have a constant c and you want to find the derivative of c f x, then you just need to differentiate the f(x). And since c is constant, you can just bring that out of the differentiation operation. Okay, so the constant will not affect the differentiation. Let's consider the following example. Let's find derivative of 5x cubed, right? So since 5 is constant, I take that out. I have 5x cubed derivative. And I use the power rule for x cubed. I have 5 times 3 times x 3 minus 1. Okay, so I have 15x squared. Okay, at this moment, I will do this operation minus, because we know that, when we apply the power rule, the power will be decreased on 1 unit. But, in the future, probably we will not do that all the time. Okay, just writing short x squared. Okay, let's consider the function 1 over 2 cube root of x squared. And let's find the derivative of this function. So, this function looks like a quotient, right? But again, we can convert such function into power function. Before that, I will take 1/2, right? We have 1/2 in here out. So I have 1 over 2. That is just coefficient. And inside, I will write 1 over x2 2 over 3, right? But what is 1 over x2? x2 2/3, right? That is just, you can write x negative 2/3 in here, and then derivative. Does that make sense? And then you use the power rule. 1 over 2 times, you take the power, this one, down here, you have times negative 2/3, and then multiply with the x. Here, the degree will, the power will decrease by 1 unit, right? So I have 1/2 with the 2, that will be cancelled out. I have negative 1/3, and x negative 5 over 3. Or if you want, you can rewrite that is 1 over 3 times x to 5 over 3. Okay, again, right, we do this technique several times, and in previous lecture we also convert such function into power. Okay, so we need to pay attention on this. Now let's solve some tangent line problem. Example 2. Let's find an equation of the tangent line to the graph of the function y equal to 3x to the 4 minus 3x plus 1 at x equal to 1. Okay, so we know in this case we need to find the derivative of the function, but our function is not like single functions, right? You have single terms like this, like this, like this. You know how to find derivative, right, of each term. But now you have difference or sum of such terms. So how to do that? Again, in this situation, we need to apply the sum or difference rule, right? different rule. I'll tell you, this is pretty easy because it comes from the definition of the derivative. So that's why I don't write it in separate form. But if you have two functions f and g, right, and you want to find the derivative of f and g plus g or f minus g, so you just write that is f derivative plus or minus g derivative. Okay, so it's pretty easy. If we apply this rule for this function, we have derivative of our function y prime equal to 3x to the 4 derivative minus 3x derivative plus 1 derivative. Look at this. Now I can rewrite that is 3x to the 4 derivative, right? Because that is just coefficient minus 3 times x derivative and plus 1 derivative. All right, we know how to differentiate x to the 4 and x, right? X to the 4 derivative is 3 times 4, and then here is x cube, right? Because you take the power of 4 down and then you decrease the power by 1, right? And since x is x to the 1, right, then x derivative is x to the 1 minus 1, which is x to 0, and that is 1. You see, you use the power rule, so the derivative of x is just 1. I write 3 times 1, and what is 1 derivative? That is 0. Why? Because if you differentiate any constant, right, any constant, you differentiate that, you get 0, because the function does not change. So if the function does not change, so the rate of change should be 0. Does that make sense? From this observation you have, that is just 12x cubed minus 3. And that is your derivative. Okay. Once we have derivative, we can plug the point into the derivative to find the slope, right? We are considering point x equal to 1. So I can write slope equal to 12 times 1 cubed minus 3, which is 12 minus 3 is 9. Perfect. We have slope, we have the point, right? But again, right, we need, since we didn't have the y coordinate of the x, so when x equal to 1, I can find the y of 1 is, I plug 1 into the function. Where's the function? The function is right here. Let me calculate in here, right? Y of 1 equal to 3 times 1 to the 4 minus 3 times 1 plus 1. That is just 1. So y1 is 1. Then the equation of the tangent line looks like y minus 1 equal to the slope times x minus 1. Or you might simplify, you get y equal to 9x minus 8. And that is the equation of the tangent line. You see, each time when you need to work with the tangent line, you have to work with the derivative. And so you need to know how to differentiate functions. Okay. Now let's consider another example, and I think that is also a very typical one. You have function y equal to 3x squared minus x plus 1 over x. You need to find the derivative of this function. Okay. So you see again, right, the function is fractional, right? Or we say rational. You have one function divided by another. We don't know the quotient rule, we don't know how to find the derivative of this function, right, if we don't change it. So in this situation, I will break this function into 3 functions, because on the top you have 3 terms, right? And in here you have only 1 term. So we can break this into 3 functions as 3x squared over x minus x over x, and then plus 1 over x. You see, it is pretty easy, right? And you rewrite all terms in the power form. So I have 3x from here I have 1, and 1 over x is plus x2 negative 1. And now you use the sum and difference rule to differentiate this function, right? From here you get y prime equal to 3x derivative minus 1 derivative plus x2 negative 1 derivative. And 3x derivative is 3 times x derivative. Derivative of 1 is 0 because 1 is constant, right? I write 0 in here. And here, if you remember, you can write negative 1 over x squared right away, right? But if you don't remember, you can use the power rule. You write negative 1 in here and then x2 negative 2. Okay, so I have 3 because the derivative of x is just 1. So I have 3 minus 1 over x squared. That is the derivative of the original function. You see, sometimes we have to do that. And I tell you, right, breaking a function into different functions is also one of important techniques, not only for differentiation rules. When we study integrations, sometimes we need to do that because we don't know how to integrate this function, right, in general. But if you can break this function into power functions, we will have power rule for integration. So this technique is quite popular. I'll tell you this, right? Okay, so I think with basic rules, with basic differentiation rules, we are okay now. We know how to differentiate a constant. We know how to differentiate a power function, and we know how to convert, right, some simple functions into power, like radical functions and fractional functions, like this, right? So like this radical function in here, you convert this into the power function, and then again, right, you convert into this form, so you differentiate that. Everything's good with such function. Okay, now we move to the rate of change. We have derivatives of sine and cosine functions, but I will make a video separately, a separate video for differentiation of trigonometric functions, so we will not consider in this video. Let's move to rates of change. Just consider one or two examples about this, because we were talking a lot about the derivative, right? We know the derivative is rate of change, right? And in the tangent line problem, the derivative is the slope of the tangent line, right? So we solve many problems regarding the tangent line. Let's solve at least one problem about the rate of change. Okay, so again, let me remind you, we have two rates of change. The first rate of change is the average rate of change. So what is that? That is f of b minus f of a over b minus a. So if you consider on some interval a and b, right, you might have the average rate of change on the whole interval. So that is the change in the function divided by the change in the variable. Okay, but again, if you want to see the instantaneous rate of change, so you need to consider the limit, and that is the derivative, right? Instantaneous rate of change. Okay, so this is nothing but derivative. I will not repeat the formula again, but basically that is from here, and you consider the limit. Okay, let's consider the following example. We have a billiard ball is dropped from a height of 100 feet. Okay, and then we know the ball's height s at the time t is the function s equal to negative 16t squared plus 100, where s is measured in feet, okay, this in feet, and t is in second. They ask us to find the average velocity. The first question, find the average velocity on 1, 2. Okay. The second question, find the speed. Or I can write here instantaneous, right? Instantaneous velocity at t equal to 2. Okay, so look at this. So imagine about it, right? You drop a ball from the height 100 feet. So this is, the pole. You drop that, the ball is falling down, okay? And the position or the height can be measured as, a function, right? That is negative 16t squared plus 100. We have negative over there because, the ball is falling down. That's why we have negative, okay? So the highest one when t is equal to 0 would be, 100, right? 100 feet. That is the time for t equal to 0. So they ask us to find the average velocity on the interval 1, 2, means suppose when this is t equal to 1 and then this is t equal to 2, right? We need to find the average velocity. That means the average rate of change, right? Look at this. The average velocity means the average rate of change. Okay, and then they ask us about the speed when t equal to 2, means the instantaneous velocity or the instantaneous rate of change at t equal to 2. So that means they ask us about the v, right? At this moment, you see, when you ride a car, right? You can see the speed you see on your car is the instantaneous velocity. That is not the average velocity. Don't forget that. So in that case, we need to find the derivative, right? The derivative. That's it. Okay, so let's find the average velocity. Here's my solution. Average velocity on 1, 2 is equal to f of 2 minus f of 1 divided by 1 minus 2, right? And you plug 1, 2 into the function, you get negative 16 times 2 squared plus 100, right? Minus, I use parentheses, 16 negative in here times 1 square plus 100 divided by 1. So I have 100 will be cancelled out because you have plus 100 in here and plus with the negative, right? So that will be cancelled out. I have negative 16 times 4 plus 16. So basically I have negative 48. That is the average velocity. We have negative because, again, the ball is falling down, right? Now, let's talk about the instantaneous rate of change. Means the speed, the velocity at t equal to 2. So I have to find derivative, right? Derivative. F prime t. I need to apply the power rule for this function because we have power in here. The derivative of 100 is 0. So I just need to find derivative of negative 16t squared. Okay, so that is negative 16t squared. Anyway, I write here plus 100 derivative. That is negative 16 times t squared derivative plus 100 derivative. I have negative 16 in here times 2 times t, right? Plus 0. So I have negative 32t. You see, that is the general formula of the instantaneous velocity or instantaneous rate of change. So when t equal to 2, right, I have derivative at 2. That is negative 32 times 2, which is negative 64. If you compare negative 64 with negative 48, you can see something, strange, right? But that is normal. Why? Because the ball is falling down. The ball is falling down. Negative 40 is the average velocity on the whole interval. Is that correct? So usually, at this point, the velocity is less than negative 48, and at this you have negative 64, right? Because this is much bigger than the average. Because at the beginning, you have a smaller velocity. Is that correct? So everything is okay. Everything makes sense. That's not something strange. All right. So that is how we can look at the rate of change, like average velocity or instantaneous velocity. So I think I stop my video in here. If you have any questions, please feel free to let me know. All right. Thank you.